Hello, I'm Trevor, and I've done my testing system project on testing common rail diesel solenoid injector currents at idle. The piece or pieces of equipment that will be coming in contact in this scenario is a fleet of 7 similarly equipped 2013 Autocar Expediter refuse trucks. The trucks are all equipped with Cummins ISX-12 and 4000 series Allison transmissions. All trucks in their fleet are normally centrally fueled and maintained in-house. The client is complaining of an abnormal idle and violent shaking when in neutral. These symptoms are present in 4 of the 7 similarly equipped trucks in their fleet. When the symptoms are present, the trucks do not provide any abnormal dash lights or malfunction indicator lights to aid in diagnostics. However, the malfunctions seem to disappear entirely when the engine is at higher RPM and when moving under load. Due to the fact that the equipment's symptoms are only at idle, the client has been running the trucks on their regular routes. They have done what they can to try to diagnose the issues in-house with the limited resources they have, but they have realized it's a problem as the symptoms aren't fixing themselves. The in-house technicians at the client's fleet have provided me with all recent related work history and maintenance records that they performed on the symptomatic trucks. These work procedures were then repeated and confirmed by dealership technicians. The applicable history to know is that the trucks have been scanned for fault codes and none are present, as reported with the complaint. Inside of Cummins Insight, the technicians have monitored fuel rail pressures. Both commanded and actual fuel rail pressures are in an acceptable range. Also in Insight, the injector tests have been attempted on each symptomatic truck at least twice and are failing out inconsistently at different moments, i.e. sometimes it will fail on injector 1 and sometimes on injector 6. When taking a look at the supporting systems around the injectors, I've observed that the fuel filters have been changed regularly at recommended interval. In order for me or any other technician to perform the injector current test and measurement, we will require a diagnostic computer that has the Picoscope 6 diagnostic software previously installed on it, an automotive picoscope, the Picoscope low amp clamp attachment or equivalent clamp, basic hand tools, and access to OEM resources for information on which wires will need to be individually monitored. The manpower requirement for this test is that it will require 1 technician an estimated 2 hours to do the test on a single truck. This makes for an estimated 10 hours estimated on the job time, as 5 trucks will need to have the solenoid injector current at idle procedure carried out on them. The budget for this procedure is specifically targeted on labor, as all required materials have been previously acquired, and those previous costs are reflected in the labor rate of $150 an hour. An estimated 8 hours will be spent testing the 4 malfunctioning trucks at a labor cost of $1,200. An estimated 2 hours will be spent testing the known good truck at a labor cost of $300, making for a total estimated labor cost of $1,500. The timeline for this procedure is to complete all 5 truck tests in day 1. I will begin the day by collecting known good waveforms from an asymptomatic similar truck, so one of the 3 trucks in the fleet that are not demonstrating any issues. This should take roughly 2 hours. I will then spend 2 hours on each of the 4 symptomatic trucks. In the 2 hours on each of the trucks, I will test and analyze injector waveforms. The results from day 1 will determine my action plan. The general procedure in order to measure the current draw of a common rail diesel solenoid. This procedure will need to be performed 5 times in total. The first step is to boot up Picoscope 6 diagnostic software on your diagnostic computer. The second step is to connect the low amp clamp to the automotive Picoscope's channel A. The third step is to select the 20 amp scale and zero the clamp before connecting to each individual injector supply circuit. The fourth step is to connect the clamp to individual injector supply circuits. In most cases, you will have to reference an OEM service manual. The fifth step is to start the scope so that you can view live data. Step 6 is to start the engine and allow the truck to idle. The seventh step is that with the waveforms on the screen, stop the scope in order to pause and record the readings. Step 8 is to turn the engine off. Step 9 is to examine the waveforms using the waveform buffer, waveform zoom, and waveform measurement tools. The final step is to repeat these steps on each injector of the engine. For this specific procedure, it will be necessary to add some steps in order to gain access to the necessary wires for measurement. Step 1 to gain access to the injector supply wiring of an ISX12 is to disconnect the internal actuator harness pass-through connector. The second step is to carefully disassemble the covering and sleeving of the harness and temporarily discard. The third step is to identify wires linked to the injector supply circuit. In this case, it will be pin 1, 3, 5, 7, 11, and 15 of the pass-through connector are the wires that provide injector supply. Step 4 is to then take the previously identified wire and attach the low amp clamp to said wire. Step 5 is to reinsert the pass-through connector into its socket with the sleeving still removed. Step 6 is to run necessary tests. Once the procedure has been completed, you will need to reassemble the internal actuator pass-through connector and reinstall. The Pico Auto website does not always have the exact example waveform to compare to in all situations. In our scenario, we could not locate a comparable wavelength, so we had to source our own. We sourced ours from a similarly equipped truck that is operating without symptoms within the client's own fleet. As you can see by the example wavelength, we are at low idle. The injectors are actuating 2 pilot injections and a final main injection, as is intended by the manufacturer. Our issues are present only at engine low idle, so that is the area we will focus the bulk of our efforts on and the majority of our allotted time. Through analysis of the results of the wavelength recordings that we took from 4 symptomatic trucks and 1 known good truck, we can compare the known good wavelengths with the symptomatic truck. From this analysis, I have found that all 5 trucks tested have injectors that are operating as intended and share similar wavelength characteristics. This can be seen through the nearly identical wavelength captures, in which the injections are lasting a similar duration of time and reaching similar amplitude. Due to this, it can be concluded that further diagnostics will be necessary, as injectors are not to blame for the rough, abnormal idle, and shaking symptoms. Through our tests, it is apparent that this complaint is definitely affecting the operability of symptomatic trucks. The course of action that I recommend in this case is that we should collect fuel samples from the central fueling tanks and from symptomatic trucks. Pending the results of the fuel sample tests and the go-ahead from the client, I would then recommend that fuel tanks of affected trucks be drained, depending on fuel condition, either dispose of or treat fuel, change fuel filters in symptomatic trucks to remove as much contamination from the fuel system as possible, and replace removed fuel with a known, good, and time-tested supply. I would then conclude by verifying the fuel quality was the issue, and if it isn't, adjust my action plan and measurement system accordingly. This concludes my presentation. Thank you for taking the time to view it.